Good morning, good afternoon, good night, everyone. Welcome to this fourth webinar of the second edition of the GAWTEC webinars, which is focused on reactive gases. Today we have Martin Steinbacher as our speaker, and he will be talking about carbon monoxide in the atmosphere and measurement techniques. Before we start with Martin's presentation, I will read you, as always, the code of conduct. Please be polite and respectful to the speaker and to all the participants. Please type your questions in the chat box during the presentation, and after the presentation, we'll have a short Q&A where your questions will be answered. We are now recording all contents in presentation, Q&A, and messages in the chat box. So by joining, you express your consent. And then tomorrow I will upload this video to the ES YouTube channel, and it will be also available in the GAWTEC YouTube channel. Now I give the floor to Sonia, who will introduce our speaker today.
Thank you. Welcome, everyone. Our speaker today is Martin Steinbacher. Some facts about him. He did his diploma in meteorology in 2000 at the University of Frankfurt in Germany, and in 2004 a PhD thesis in natural sciences at the ETH Zurich in Switzerland, and in 2008 postgraduate diploma in advanced studies in environmental diplomacy and at the University of Geneva, also in Switzerland. He worked from 2001 to 2004 as a research fellow at the Laboratory for Atmospheric Chemistry at Paul Scherrer Institute in Switzerland. And from 2004 till present, he's a senior scientist at the Laboratory for Air Pollution and Environmental Technology called EMPA, also in Switzerland. His main duties, he's principal operator of the Swiss National Air Pollution Monitoring Network's air quality observation at the High Altitude Research Station Jungfraujoch, and he's also manager of the Quality Assurance and Science Activity Center Switzerland in support of WMO's Global Atmosphere Watch program. And he's also a lecturer at previous GAWTEC courses. His topic today is carbon monoxide in the atmosphere, measurement techniques. We're very happy that you're here today, Martin. Thank you, and the floor is yours.
Okay, thank you, Sonia, for the nice introduction. Let me share my screen. You should be able to see it now, right?
Yes.
Okay, great. Okay. Good morning, good afternoon, good evening, everybody. Hello, everybody. As Sonia said, the title of my presentation today is Carbon Monoxide in the Atmosphere, and I will mainly talk about the different measurement techniques that exist. Let me see why I can't. Ah, here we are. Okay. Well, I think I can skip more or less this slide already. Sonia mentioned my brief CV already. I would maybe like to acknowledge the, change my pointer. Yeah. I would like to acknowledge Meteor Swiss, that is strongly supporting the QSAC, the Quality Assurance Science Activity Center Switzerland, the center which I'm leading. And since 2008, I'm regularly involved in teaching at the GAWTEC courses, usually in person at the Zugspitze, and now it's my second time giving a virtual presentation. So today's topic is carbon monoxide, and I would like to start off with a couple of numbers. Where's the carbon monoxide in the atmosphere coming from? The main sources are anthropogenic, of anthropogenic origin. It's mainly combustion of fossil fuels and biofuels. It's about 700 teragram CO per year. Then biomass burning is nearly as large as that. And then a couple of minor or smaller sources like oceanic and biogenic sources. And then the kind of secondary origin is the oxidation of methane and hydrocarbons in the atmosphere. In total, we have about 2,600 teragram of CO per year that are emitting into the atmosphere. Okay, well, I thought it's maybe of interest for you to see some numbers. The sketch now on the right shows a couple of different budgets from different publications, all summarized in the paper by Park et al. I will have at the very end, I will have a list with all full references when you are, if you are interested in looking into these publications at a later time. And there, these graphs give you a kind of a flavor about the uncertainties of these numbers. There are a couple of different publications in the early 2000s mainly that come up with slightly different numbers, and the lower panel here shows you the total numbers, and this is, as you see, this varies maybe about from 2,200 to 2,800 teragram of CO per year, depending on the study and the inventories that are used. The sinks of CO, most of the CO in the atmosphere is oxidized by OH radicals. A smaller part is taken up by the soils, and even smaller part is going into the stratosphere and is destroyed there. If CO is oxidized by OH, finally there's a couple of reactions that are followed after the oxidation, and ultimately CO is oxidized to CO2. That's why here we are. CO, to summarize that in one sentence, CO plays an important role in atmospheric chemistry, the carbon cycle, and also the Earth radiative budget. When we look at the global distribution where the CO is emitted into the atmosphere, we can have a look at this figure from the EDGAR emission database. There you see that the most reddish areas are where the most people are living, and then we have also these biomass burning areas like in sub-Saharan Africa or in South America, and you can also nicely see the intercontinental traffic corridors where the CO emissions are also happening. A couple of numbers about the concentration, so the CO mole fractions in the atmosphere. The natural background in the atmosphere is about 40 to 200 ppb, parts per billion, and it can be maybe the double at close to the traffic, to curbside stations. Then in homes, it can vary up to a couple of ppm, depending of the sources in the homes. Like when there's a purely adjusted stove, you can reach up to 30 ppm maybe. But 30 ppm is still corresponds to the threshold limit values at workplace. For example, in Germany, that means usually you can be exposed to these numbers for at least 8 hours, and that 200 days or 250 days a year without any serious adverse health effects. Well, undiluted car exhaust, we can reach up to 4,000 ppm, cigarette smoke up to 40,000 ppm. Well, these numbers can also vary quite a bit. And maybe at around 10,000 parts per million, it really starts to be seriously dangerous for the health. This figure on the top left is a graph from the World Data Center for Greenhouse Gases data summary from last year. This data summary is compiled every year, and there this kind of confirms the first numbers given on the right, 40 to 200 ppm. This is based on global atmosphere watch stations, which are traditionally usually in kind of pristine environments. And there we see in the southern hemisphere bluish colors around 40 ppm. The northern hemisphere we see reddish and then more orange colors in the more recent past, and we see this north-south gradient that is typical for trace gases that have major sources, major anthropogenic sources, and usually then most of the sources are happening in the northern hemisphere because more people live in the northern hemisphere than the southern hemisphere. And if we look at the global mean numbers, there is from the same data summary, there we see that there's a slight negative trend, that the CO concentrations are slightly coming down over the last 30 years. And this is also seen on the top here, where we see that the reddish colors kind of disappear and they're more now in the orange range. Well, that's the last slide of my introduction. Why we are interested in CO measurements. CO is a good tracer for anthropogenic pollution and biomass burning. The sources of CO are known rather well, and putting these then CO measurements in relation to other measurements of trace gases where the sources are less well known, we can kind of estimate the emission rates of other trace gases. CO is an intermediate product of the the degradation of volatile organic compounds on the way to CO2. And as briefly mentioned before, CO can cause adverse health effects under highly polluted conditions, about more than, let's say, 10,000 ppm. There's an interesting read if you look into that paper that's from 1912, I suppose, where the mice and birds were used to detect carbon monoxide, and they were exposed to different levels of CO, and that's where very early kind of one of the first measurement techniques to detect CO, by the way. When we go to the more recent past, CO is maybe one of the trace gases that can be measured by the largest number of different measurement techniques, at least the measurement techniques that are really also applied in atmospheric sciences. And this is kind of chronologically here, starting with the Manometric Technique developed by Karl Brenninkmeier in the early 90s, and then going further down to some recent developments, mainly laser spectroscopy let's say in the last 10 years. And now I will go through a couple of these techniques, the ones that are most common or were most common in the last, let's say, 20 years to measure CO in the atmosphere. Okay, well, there are two fundamental differences. The first two techniques are kind of discontinuous techniques, because you need to collect the sample first before you can analyze it, while the other techniques on the bottom here are really continuous measurements where you can record the CO levels in 1 second time resolution or even faster. And that's why I would like to present two of these discontinuous techniques. Well, they're often pretty bulky. That's a gas chromatograph at one of our stations in Switzerland. But I would like to start with the manometric technique developed by Karl Brenninkmeier. And you can see already in that scheme that is a pretty complex system. There's the collected air sample in that cylinder here, and then it passes through quite some different traps, and first it removes all the CO2, and then it converts the CO into CO2 with an iodine pentoxide reagent, and then it is cryogenically collected. And the beauty of this system is that finally the CO2, which is only the converted CO into CO2, is measured with a manometer, and it's simply the pressure of that remaining CO2 is measured, and that's why it can be measured in absolute terms. That in theory it doesn't need a calibration, and I will come to that later today. That calibration of most of the systems is really key, even if modern techniques might even pretend that the calibration is even not necessary. And well, there you can really boil the measurements down to SI units and determine the pressure of the CO that was converted finally to CO2. Gas chromatography, I suppose that most of you are familiar with gas chromatography. Just one overview slide how that works. Usually you have an air sample with all kinds of different molecules. To take a sample, you push that with the carrier gas through a separation column, and depending on the affinity of the different molecules to the stationary phase, usually either these separations columns are filled with some grains that to have a as large surface as possible, or very thin capillary columns, and then the same thing happens on the inner surface of these very thin columns. And then depending on the affinity, different compounds exit the separation column earlier or later. And then if you have a detector, a suitable detector that is sensitive to the species you're interested in, you can get all kind of different peaks. That's now a chromatogram for volatile organic compounds. Well, it's most likely impossible to read here, but this is about 90 minutes. It takes 1.5 hours until all these compounds are passing through this separation column and detected by the detector. And that's why it's also a discontinuous technique, because you cannot measure with a very high time resolution. For CO, gas chromatography with CO, there are two main detection techniques. One is flame ionization detection. The other is a reduction gas detection. I would like to show the first one here. This flame ionization detector is usually most sensitive to CH and CC bonds, compounds with CH and CC bonds. That's why the CO needs first to be converted to methane. This is done here with a heated nickel catalyst that uses the hydrogen. In this FID, there's a flame, and then you look at the properties of the flame when the eluent of what comes out of this separation columns reaches the detector. And there you need hydrogen and synthetic air to burn the flame. And usually you use the hydrogen, passing that over the nickel catalyst, mixing that with the eluent from this analytical column, and then you convert the CO to methane, and the FID is very sensitive to methane concentrations. And this is how a chromatogram then looks like. Usually you can measure several species again. You measure the methane, and once the methane came out, you switch this valve down here, you pass the eluent from the analytical column over the nickel catalyst, and then you can get the CO that was converted to CH4 before it was detected by the FID. And there you see this is in seconds down here. It takes about 120 seconds till methane and CO is detected, and then usually you backflush the columns that columns are clean again before you inject the next sample, and usually you need to fill the sample loop SL here, and that's why usually it takes about 5 to 10 minutes for one single shot of measurements. And as you can see here, the methane and CO concentration depends, or the size of the curve under the curve, the area under the curve is a proxy for the concentration of methane and CO in here. And here it is kind of trivial that you need to calibrate that system very, very often. That means you need to inject reference gas with known amounts of methane and CO to determine the relationship between the area under the curve and the CO concentration. Usually, in this case, we even did that every second measurement, every ambient air measurement was bracketed by a calibration. Okay, from the discontinuous techniques to the more modern techniques, most of them are continuous. For many years, NDIR, non-dispersive infrared spectrometry, was the most common technique. And what is schematically shown here is kind of similar for most of the other techniques that I will show later today. Usually you have a light source, you have a cell where the light interacts with the air in the cell, and then you have a detector. And here it is for NDIR, as the name it says already, it's an infrared radiation, and then, well, you focus the light and then you pass over the sample. And there are two different techniques to really put that into practice. I will show both of them in the next two slides. And the advantage here is that they're rather inexpensive, and it doesn't need a lot of attention. Operation is pretty easy, and it does not need a lot of maintenance. But the disadvantage is that the noise of the instrument is rather high. The detection limit is rather high, a few tenths of ppb, and if I suppose that you can remember, the southern hemisphere numbers are on the order of 40 ppb, then we nearly reached the detection limit there, and this technique is often prone to instrumental drifts. NDIR is most suitable for sites with somewhat elevated concentrations and less so at remote sites, as I said, because of the rather high detection limit. Okay, well, this is usually the time when we leave the classroom during this GAWTEC course, and we enter the lab and we look into one of these analyzers. Since we cannot do that here, I tried to animate that a little bit. We see a schematic here of one of these instruments. This is now with the gas filter correlation. That's a measurement cell here. You have the infrared source, you have the detector, and then you have a gas filter wheel here that turns very, very rapidly, and that is partly filled with nitrogen and partly filled with pure CO. And that allows to every time it turns to get a reference beam when it passes like that through the wheel when there's the part with the pure CO, and then the measure beam when it passes when there's the segment with the nitrogen. And that allows to correct for interfering species. Okay, that turns pretty rapidly, and well, usually we are in the lab and we look into the instrument and we compare with the schematic. Anyway, every measurement technique you use, I really suggest to properly read the manual, look into the schematics, maybe also have a look into the instrument and to try to understand how the instrument works and what the different parts of the instrument are good for. The other realization of this NDIR technique is the cross-flow modulation. There we have a pump in here, and either the pump sucks the sample in here, there's a filter, a mist catcher to remove part of the humidity, and then here's the analysis going on, or the valve switches here, and then the air that passed the cell before is passing a catalyst, and all CO is oxidized to CO2, and then it measures a sample without CO, but the whole other matrix of the sample still remains the same. This is realized by Fourier like that. And both instruments with that compensation should respond specifically to CO in theory. But in practice, there are still some interferences going on, and also the the background noise is rather high. Here we see from a paper by my colleague Christoph Zellweger from 2009 for two months. We see our zero checks that are done every 2 days, every 49 hours usually. And if you look at the 1 minute values, we see that this can scatter from, let's say, -20 to +20 ppb. It gets much better when we look at the 30-minute averages, but still there's some variability here that is, well, still about 10 ppb or even more that can vary here within a couple of days. And this is something that is known, or well, at least known to experienced users, that these NDIR techniques are prone to instrumental drifts, and this depends somewhat on the manufacturer and the way how this NDIR technique is really implemented. And there we see that for one instrument, the zero drift is rather small, but for others, this is now for 6 weeks about that there's a drift of a few ppb per hour that can be seen when really doing these zero checks every couple of hours. And I would like just, well, okay, depending on the instrument and the laboratory conditions, the zeroing needs to be performed very, very frequently, every few hours. And I would like to recall, I didn't mention that yet, but according to the greenhouse gas measurement techniques meeting report that is released by WMO every 2nd year, where we define some network compatibility goals. The data quality objectives for CO are on the order of 2 ppb. And if you have drifts of a couple of 2 ppbs per hour, you can see that if you want to correct for that, you really need to make a zero very frequently every few hours. And that's a bit cumbersome, but the good thing is that you can generate your CO-free air on site next to your instrument. Usually, there's a kind of a zero air unit. The only thing you need is a heated oxidation catalyst and/or a cartridge with some powder that converts CO to CO2. And this is then how it looks like. Usually you measure your ambient air, then you switch to zero. You need to wait for sure a couple of minutes, let's say. Sometimes it's just followed by a reference tank, and then you switch back to ambient air. But you should be careful when using commercially available zero air generators, because they're often not optimized for CO removal. Often it is first, like you can see here, this is one of these heated catalysts, heated to 450 degrees, and then it is passing some other cartridges that are supposed to remove hydrocarbons or nitrogen oxides, and sometimes in these cartridges you produce CO again, and that's why usually the last thing in the series should be kind of something like a softener cat powder that removes all the remaining CO. Okay, well, more advanced, or it was a big step forward in terms of measurement precision, is this vacuum UV resonance fluorescence technique that was developed in the late 1990s. The measurement principle here is you have a lamp, and then you excite the CO in that CO is here in that cell, and then you excite the CO, and you measure the fluorescence of the excited CO here with a photon multiplier. That is very fast, precise, and very linear, but the instrument is pretty expensive, has delicate optics, and it needs also some special gases like argon and CO2, which is maybe not easily available in some countries, some regions in the world. And that was, well, this was often used for mobile measurements, also for aircraft measurements, because it was so fast, or it is so fast. Okay, well, now most of the more recent techniques are based on laser absorption spectroscopy. That's why I added this slide here. Again, you have a light source, in this case, a quantum cascade laser. You have a measurement cell, you have a detector, and then some air in, air out, some pumps. You flush the cell continuously. And then you see here an absorption spectrum, in this case for N2O in red and CO in green. And there you see that, and water vapor in blue. And there you see some nice absorption features. And if you have a laser that is emitting light in the right wavelength region, you can very nicely and very precisely determine even various trace gases with one shot, with one instrument, and these instruments are also very fast. It is most efficient in the mid-infrared region, near to mid-infrared region, and at least in the beginning, in the early phases of these instruments, you see that's a liquid nitrogen duo here. These lasers had to be cooled with liquid nitrogen, which is kind of unsuitable for long-term monitoring. But with the years, there was quite some progress made, and now this is different ways how you can optimize this to measure the laser absorption spectroscopy. And there we see one way how to do that is so-called off-axis ICOS, off-axis integrated cavity output spectroscopy. There you see that the laser is somewhat tilted by purpose. And then you have some higher reflectivity mirrors with a reflectivity of more than 99.99%. And then the light bounces back and forth. That helps improving the precision, because then the light beam, the path length is way longer than the cell that is maybe 20 centimeters long. And after many reflections, the light hits the detector, and then you can get these absorption spectra. But you can measure several trace gases at the same time, depending on the wavelength range you're looking at. And it's very rapid and doesn't need any liquid nitrogen anymore. And well, it's measures in the mid-infrared. One of the common instruments that is used in long-term monitoring is built by Los Gatos Research in California. Another manufacturer, well, first of all, I thought not to mention any manufacturer at all, but when preparing the slides, I realized that it won't work. And anyway, if you look into the literature, you will easily see which instruments are used. And I do not make any recommendation for a specific manufacturer, but I thought it is, well, it will make most use for you guys when I even add the URLs where you can browse and see, and you can learn more about the different techniques. Another manufacturer, it's Aerodyne Research on the US East Coast, that is doing pretty similar things like the instrument we have seen before. You have a measurement cell and a laser, and then it bounces back and forth. The nice thing here is that it is a kind of modular system, and you can also even have two lasers that emit light into the measurement cell, and then that means that you can increase the number of parameters you want to measure. You can measure with one single instrument at the same time. And as I said, it's a little bit a modular system. There you can, on the web page, you can see that you can select different combinations of parameters depending on the laser that is used, and then you can measure up to 4 or 5 parameters, let's say. Picaro, it's another company in California. They well, they also do laser spectroscopy, but they do it a little bit different than the others before. They call it cavity ring down spectroscopy. There you have a laser here, the detector here, and the light bounces in a triangular shape here, reaches the detector, but here the laser is turned off, on and off very rapidly, and then what happens when the laser is shut off, then the light still bounces here in a triangular way, but the signal kind of rings down. That's why it's called cavity ring down spectroscopy. And depending on the concentration of the molecule of interest here in the cell, if there's a lot of, let's say, CO in the measurement cell, and you look at the right wavelength, then the laser signal will ring down more rapidly than in case when there's hardly any or there's less CO in it. And that means the ring down time is a proxy for the CO concentration in the measurement cell. And usually the measurement cell is continuously flushed with the sample. Okay, what's next? That's Fourier transform infrared FTIR spectroscopy. Again, it's you have a light source in the infrared region, but it's kind of broadband. And here on the top right, you see again an absorption spectrum, but in contrast to the one before, where we have only seen one or two N2O and one or two CO peaks. You see it's broadband, and then hopefully you can read that is CO, N2O, 13 CO2, 12 CO2, HDO, methane, water, CO2. This can be all measured here with that this instrument. That makes it pretty attractive, because then you can have 5 or 6 species with one instrument. The downside is it's a bit bulky, and it requires nitrogen as a purge gas. Gaseous nitrogen should be usually available everywhere, but for sure, I know that this is can be a tedious job to transport high pressure cylinders to measurement stations, especially in pristine areas where transport and access is maybe limited for some time. And again, you can measure simultaneously several trace gases, as I said. Well, I do not want to forget other manufacturers. Since I started mentioning them, there are at least, well, there are more than those on the market. Some are rather new, just emerging techniques. Direct laser absorption spectroscopy, they also, mirror analytical, there you can have up to 10 parameters, I think, measured at the same time. Then Thermal Scientific developed a mid-IR absorption spectrometer. Tiger Optics is doing cavity ring down spectroscopy like we have seen before. Aris Technologies is a rather new brand that does long path tunable diode laser spectrometry. Feel free to browse the web pages. I just want to mention them here. And it's maybe also worth mentioning that long-term atmospheric monitoring is following often rather conservative approaches, and is not, well, or let's put it in other words, is measurement techniques needs to be proven that new measurement techniques are really applicable also for long-term monitoring. For sure, some of these techniques can be very precise, but if you're doing long-term monitoring measurements for decades of years, you are usually very reluctant to switch from one known type of instruments which you have experience with, and you know the downsides and the interferences and things like that. It usually takes a lot until techniques are changed, or usually you measure a couple of years maybe in parallel to be sure that there are no surprises anymore once you switch your master instrument from one technique to the other. That's why it is often it takes some time until new measurement techniques are really penetrating the long-term monitoring business, like in GAW. And a couple of words about calibration, performance, comparison of different techniques. 2 slides about the calibration. The NDIR instruments often in the past, they were just calibrated with one high-level reference gas in a ppb level, and then it was diluted with 0 air. The advantage is it requires only 1 cylinder. You can do multi-point calibrations when you change the settings of these mass flow controllers. You have different dilution ratios. You do not need a lot of calibration gas here because it's, well, you need only a couple of milliliters per minute maybe, and you dilute that with 1 or 2 liters of 0 air. And ppm level standards are also less prone to drifts. But with that setup, it is difficult to achieve the very good accuracy and the compatibility goals I mentioned before, and the direct traceability to the GAW reference scale is difficult to achieve. That's why within GAW, if you want to really do precise measurements, setup gets often more kind of complicated. You have an analyzer here, you have the air inlet here, and then you have some valve switching that allows to connect a couple of calibration gas. In this case, it is from the European ICOS project. It's 4 different calibration gases, and then the system also allows to connect a couple of other quality control cylinders. This allows direct traceability to the GAW reference scale, because you can order these calibration scales directly from the central calibration laboratory. It allows maximum accuracy and compatibility with other stations. And as I said, you can usually also connect other tanks for quality control. But then you need to inject that the air out of these high pressure cylinders directly to the instrument. It means you need more reference gases, and ppm level standards are prone to drifts. I will show that one slide in a second. A few words about the central calibration laboratory of GAW for CO2, methane, and CO. This is hosted by NOAA in Boulder in the US, and usually they maintain a suite of primary standards where they really know exactly what is in there, and then they have some secondary standards. They compare them, and then they have a third level of cylinders that can also, you see, the outside carbon cycle greenhouse gas researchers groups, which you can purchase there. And then usually, at least if you have, a network with several stations in your country, or you are in charge of several stations, you get those cylinders from the central calibration laboratory. You keep them and you compare maybe in-house those standards, and these are the standards. The in-situ standards are the ones that are used at the station for this calibration every day or every week. That means it adds another level of hierarchy of cylinders, and this is really something that you really need to take care of to properly calibrate your instruments. Modern techniques often, these absorption spectra there are databases available, and the rough numbers are usually given by the analyzers as is, but this is often it is appealing, but it is somewhat also misleading when you really try to achieve the best possible precision. There's no way. You need to calibrate, and you need to calibrate also rather often. Well, a couple of words about the drifts. These are primary standards at NOAA, the CCL. You can find this plot on their webpage, and there you see this is now for five years, and there you see in nearly all cylinders CO is increasing by about 1 ppb per year. And this is also confirmed by traveling standards that the World Calibration Center for CO, which is also hosted at AMPA. There we see this is now 4 or 5 years, and there you see also that nearly all tanks behave in a similar fashion, but the positive trend is not always the same, but it's on the order of 1 ppb per year. And this is pretty similar to the negative trend we observe in the atmosphere. That's why usually if you have cylinders from the central calibration laboratory, you need to send them back for reanalysis every couple of years. Okay, the drift in the standards, well, be cautious, and you need to keep track of those. Well, I would like to finish with a few figures from comparisons. This is a publication by Zellweger, already mentioned, from 2009. And there we see, when we start at the bottom, we see this vacuum UV resonance fluorescence in greenish colors, 10 seconds, 1 minute, and 10 minute resolution. And then the single dots are the GC measurements that are usually every 10 to 15 minutes. And then we aggregate higher aggregates, 1 minute, 10 minutes, 1 hour data. And then we also add the NDIR measurements up here. And interestingly, well, let's look at the 1 minute data. You see that the noise is way bigger for the NDIR, but when we look at the top and we look at hourly averages, well, the performance seems to be pretty similar. That means it is, well, aggregating to higher aggregates for sure will reduce the noise. And even that's at one of our high altitude stations in Switzerland, which is rather clean, the performance of the NDIR was sufficient when compared to the high precision continuous analyzer. We see some slight differences when we look into the GC techniques, because there an hourly average is just the average of maybe two single injections. Okay, these are so-called Allen variance plots, which are rather common for these fast techniques. There you see the longer you average, on the x-axis you see the time in seconds from 10 to 1,000 seconds. The longer you average, usually the smaller the standard deviation gets. This is kind of the plot on the top left, kind of follows the theory. But in practice, often there are slight instrument drifts that will result in a kind of a minimum. And there you see the minimum is the best precision you can achieve. Here it's a little bit slightly more than 1,000 seconds. Then you can get a precision of about 0.25 ppb. And there you see, I would like to put your attention to the absolute scales here. They are way different. This ERDS is performing the worst here, but you see that it doesn't show nearly any instrument drifts, while others show higher standard deviations already after a few hundred seconds. And this figure is kind of supported again here. That's just another way how this is presented. On the left side, you see the cavity ring down spectrometer in orange, the UV resonance fluorescence in gray, and there we see that the precision is much better. That's for measurement tank here, and then when we zoom in, we also see how the quantum cascade laser instruments, they even perform again better than the UV fluorescence techniques. And this is a plot from the system and performance audits of the World Calibration Center that are done. On the right-hand side, it's a zoom of the inner part here. The yellow and the green areas are the compatibility goals and the extended compatibility goals. If an instrument during the audit complies with the compatibility goals, the dot should be within the green area. And there you see that there are quite some blue numbers. This is mainly GC and NDIR techniques are somewhere on this figure, but the newer techniques are more and more reaching, complying with the compatibility goals. This is also, well, it's also kind of a temporal evolution here that, well, there's very much progress was made in the last years, and the instruments are getting better, performing better and better. Instrument precision, it's not all. That's a figure from the integrated carbon observation system in Europe, and there we see is a measurement station in the Czech Republic, and there it was switched from a quantum cascade laser to a cavity ring down instrument. Here we see this is kind of the measurement repeatability. And there we see what we have seen before. The quantum cascade laser noise is well, way smaller than the noise of the cavity down spectrometer. But when we look at the standard deviation of the atmospheric measurements, this is, well, that's now includes the atmospheric variability. We do not really see that difference anymore if we use a very high precision instrument or an instrument that has a little bit higher noise. And the CRDS instrument has a rather high noise, but it is convenient for long-term monitoring because it is pretty, the instrument sensitivity is very stable over time. Here we see 1 year of calibrations every 2 weeks, and the lower panel here shows CO, and there we see the instrument was off by 3 to 6 ppb, but well, we don't really care because we correct for that. That's why we calibrate, but there's hardly any drift, and that means even the calibration every 2 weeks is maybe, well, I fully recommend to calibrate every 2 weeks, but because you never know if there's something unexpected happening. But after 1 year of measurements, we see that there's, well, even 2 calibrations would have been maybe sufficient because there's hardly any drift. That means this cavity ring down technique is maybe less precise but very stable over time, which has also a rather big advantage. Okay, that's my last figure before I summarize. That's a very rough qualitative sketch. We see the time here, the integrating time, we see the precision, and well, we see the NDIR, which is kind of starting to be a bit outdated. Well, or it's maybe not the instrument of choice anymore for remote stations, but still a good solution for a little bit more polluted stations. And we have cavity ring down with GC techniques that have a limited temporal resolution, UV resonance, fluorescence, quantum cascade lasers. And as I think you have seen that different manufacturers finally implement these techniques differently and all have advantages and big disadvantages here. Okay, to conclude, but there are several analytic techniques that are available, or maybe even too many if you are a beginner and you want to start measurements and you do not know what to buy. And the selection of the technique strongly relies on the scientific interest, the scientific question you wanna answer. Are you interested in long-term monitoring or just campaign measurements? That this is of interest if you choose maybe an instrument that has more long-term stability or a very short-term precision. The concentration, if you really want to do measurements in the southern hemisphere at really pristine places, you need to consider a rather low detection limit. How about the capacities for operation and maintenance? Usually remote sites, this can be complicated to do a lot of maintenance very frequently. Available sample, that means the instruments have very different cell sizes. If you're short in sample, you should choose an instrument with a rather small measurement cell. Reference gases, how often you can afford to calibrate. How are your skills and expertise to run some of these rather advanced, sophisticated instruments? As I mentioned, some instruments are larger than others, and for sure some instruments are more expensive than others. There's a long list, and I think the list is even not complete. Well, if you want to start measurements, I suggest to ask your colleagues and peers and consult the literature, see how other people perform measurements in maybe similar environments where you are planning to do the measurements, and then, well, then you will hopefully make the right choice to choose the right instrument. And I would like to finish here. I think I just add here 2 slides with the references of all publications that I mentioned on one of the slides before, this and there. And I would like to thank you for your attention. Thank you.
Yes, thank you very much, Martin, for your very detailed presentation. I think we have some questions coming up. The first one is, what are typical error sources in your experience?
Error sources. Okay, I imagine that the question is about, well, measurement artifacts or something like that you can have. I didn't talk about humidity at all. That is often an issue. Some of these instruments, they have a drying system already included. Some others do measure atmospheric water vapor at the same time as that they measure CO, and then it is likely that you can correct for water vapor interferences. Well, this is maybe the one of the most obvious issues, that you should know what your instrument, how does your instrument perform when the atmospheric water vapor is changing. And usually reference gases are usually dry, because high pressure cylinders, there's hardly any water in it. Well, then changes in temperature in the laboratory change, depending on the technique, can dramatically change the sensitivity of your analyzer. And well, the weakest part is often the pumps, because they're really run 24/7 and they're getting hot. Pump failures, well, this is maybe an easy one to replace a pump, but for sure you need to identify the problem once your measurement is looking awkward. I hope that answered the question.
Great, thanks, Martin. This has been a really great talk, and I've learned a lot. I have one question for you. You made the distinction between discontinuous and continuous measurements. I think we generally think of continuous measurements as being the norm these days, but are there scenarios where discontinuous measurements make more sense? And along those lines, are there ways that one might want to combine the 2 types of measurements for some sort of scientific purpose?
Okay, well, the big advantage of discontinuous techniques is the small sample size you need. I showed a flowchart of one of our gas chromatographs. There, I didn't mention that. Maybe it was mentioned on the slide, but I'm not sure. The sample loop there is usually we use 5 to 10 milliliter sample loop. That means you need to flush the loop a little bit before, but that means you need really a tiny amount of sample to analyze, to get a pretty precise number of the CO and other trace gas concentrations. If you have a measurement cell that has a size of 1 or 2 liters, like some of these instruments have, well, then sometimes there's also a vacuum there, but still you need a significant sample size, a significant amount of sample to get a good analysis. And GC techniques are often used if you do some flask sampling at several places, and then you ship the samples to a central laboratory where you do this analysis. And usually if you have only a 2-liter flask, then still gas chromatography is still a common technique to analyze the CO concentrations. Also having in mind that you would like to make a bunch of other analysis, maybe for other trace gases.
Thank you very much. And I think we come now, there's another question just coming in. So I will ask for Sumin. For ICOS LGR, is zero test using soft no cut needed? In SW, only 1 point calibration is possible. I wonder it is correct enough.
Okay, okay. SW is the software, I think. Well, there are different approaches. You can also use a suite of calibration gases. Usually, if you calibrate, you should try to bracket the range of CO concentration that you measure in ambient air. You should bracket entirely by your calibration standards. That means if you expect concentrations between 100 and 200 parts per billion, you should have your lowest standard should be less than 100, and your highest standard should be above 200 to really cover the whole range of atmospheric observations. Low concentration, low ppb reference gases, as I said, are often changing. The concentration is changing over time. That makes it a bit difficult, and this could be overcome by really generating CO-free air on site that gives you a well fixed spot on your calibration curve at the very low end. Using only one reference tank is not enough, I would say. That's the short answer.
Okay, thank you very much, Martin, for sharing all your wisdom with us. And we will also make it available.
Great. And
this webinar series continues with the webinar by Detlef Helmich on November 10th at 2 p.m. UTC on methods for the monitoring of atmospheric volatile organic compounds. So we hope to see you all again there. And thanks again, and bye-bye. We are closing now.
Thank you. Goodbye.
Bye, everyone.